Good morning, Math 7 students, or whatever time of the day you're watching it. I'm recording in the morning. But this week, we're going to try a little bit of a different format. So first new thing is we're going to do a little bit of a warm-up that kind of reflects back on last week's topic. So kind of a chance to brush up on that, reactivate your knowledge, and kind of a hint that if maybe you're struggling with the warm-up to go back to last week's and just like brush up on it first. So go ahead. I think it'd be beneficial to just pause this video, try this problem, but I'll kind of keep talking. So as soon as you come back, we'll go through this problem and check up. So we'll be going through 5.5, 5.6 this week. So first we'll go ahead and solve this one. So we got x plus 12 is greater than or equal to 9. And so what we're going to do is we'll just balance it out just like we do if this were an equal sign here. We'll undo the addition, subtract off 12 from both sides, cancel it out on the left-hand side, and we get x is greater than or equal to negative 3. And then we just come over here, kind of graph our solutions. And if we do that, well, we've got a solution at negative 3. So we'll go ahead and fill that in. So that says are or equal to, could be equal to negative 3. And it also says it's greater than. So we'll shade to the right. So again, if you need kind of a brush up, go up to last week's video, but we're going to go ahead and jump in. So goals for today is we're going to try to set up, solve, and graph some more complex inequality problems. And we're going to try to use the balance method. And this seems more intuitive than it is, but there is going to be a really weird rule with the balance method when it comes to multiplying or dividing by a negative. So we'll see that soon. So first problem we're going to jump into, or first main problem, is this problem that I gave to you last Friday. So we're going to look at this. A lot of you kind of solved it using one method, but there is quite a lot that could be gleaned from this problem. So we're going to start just, we've got that inequality. And again, if you haven't done this yet, you can just do it real quick if you didn't do it last Friday. But we've got this inequality. We've got negative 6x is greater than 24. And we got two students that are arguing two different things. Alex argues that x is greater than negative 4, and Hope argues that it's less than negative 4. So if you use the balance method, you probably agree with Alex's work. But if you used the test cases, kind of, I'll show you how that works. But if you use kind of just like your brute force test cases, you'd find that Hope is correct. So let's jump in and see what that looks like. So what I'm going to do is I'm just going to test a few points. So we're trying to figure out what x could be in this inequality. So we're going to try a few numbers. Let's try like negative 6, negative 5, negative 4. And we know 6 times 4 is 24. Negative 6 times negative 4 is positive 24. So we're going to kind of hover around negative 4. And let's try a few things to the right of it as well. So we're going to go in, I'll do the first one kind of real explicitly, and then the other ones will just kind of write in. But let's try what if x is equal to negative 6. We'll look at this case right here. So if x is equal to negative 6, we just plug that in. So we get negative 6 times our variable, which is now negative 6, is greater than 24. So if you get negative 6 times negative 6, that's negative times a negative, which is a positive, and 6 times 6 is 36. And so you get this statement, 36 is greater than 24. And I think we can all definitively say, yes, that's true. So if an inequality is, or if x is negative 6, we get 36 is greater than 24, and that's true. We could similarly, if we plug in a negative 5, we would just get a negative 5 right here, and we get negative 6 times negative 5, we would get 30 is greater than 24. Plug in a 24, let's state that it's true first. Here, if we plug a negative 4 in here, we get 24 is greater than 24. So those are actually equal. So that is tempting to say it's true, but it's false. 24 is not greater than 24. If we plug in a negative 3, we'd get negative 6 times negative 3, which would give us 18. And the statement 18 is greater than 24, that is also false. And let's just do the last one for completeness sake. -2 times -6 would give you 12, greater than 24, also false. So you could put this on a number line, and let's go ahead and do it. So let's plot kind of a number line using our test cases. And let's plot what we know. So we know -6, that's true. Let's fill it in. We know -5. We know that's also true. Let's fill it in. -4. We know that's not true. -3. We know that's not true. And -2, we also know that's not true. And we kind of overlay this and we say, well, as long as we go like ever so slightly in this direction, if we did like -4.1, we'd also be true. So anything just to the left here, let's just fill it all in. So we've got this inequality here, which basically is the statement x is less than -4. And from here, we're going about the most direct method possible, so we can be pretty confident that this is true. So we're kind of definitively saying, Hope's work, that's the correct one. However, what do we think Alex did? So let's try the balance method and see what's happened. So did Alex just misapply the balance method, or is something else at play here? So I'm going to take the original inequality method and we're just going to go at it like we normally would. So -6x greater than 24. So I'm going to go here and say, well, I've got multiplication here. Let's undo it with division. And I divide by -6 and I divide by -6. Here they'll cancel out. I get x, and let's keep the greater than symbol. 24 divided by -6. Well, 24 divided by 6 is 4, and it's a positive divided by a negative, so the answer must be negative. And we get x is greater than -4. However, that is not only not the solution that we found to be true, it is exactly the opposite. So I'm going to unveil a rule here, and this is kind of what happened, but notice we got the exact opposite. And as long as we just had the opposite symbol here, it would have been exactly the same as what we found to be true. So the rule here is, and we'll explain why in a second here, but if I multiply or divide by a negative number, I have to flip the inequality. So at this step, I divided by a negative number, I have to flip it. And that's going to seem very strange. It's going to seem very like out of the ordinary. So I want to try to explain why. So just to kind of clarify, this is going beyond Math 7. So really all Math 7 kind of does is we know this as a rule because we can try it and we can see that it holds true, that if we multiply or divide by a negative number, I have to flip the inequality for it to hold true. But I'm going to try to go above and beyond because I don't like giving you things that don't really have a reason by it. And I think we have the tools to kind of analyze it. So I'm going to use kind of what we use to introduce the balance method, is it's kind of like a teeter-totter. So let's take a look at what happens when we look at this from an equation standpoint. So what I'm going to do is I'm going to treat kind of equations as a teeter-totter. And a teeter-totter is a great kind of real-life example of like something being equal to each other. So when this is exactly like so, we know that this left-hand side is exactly the same weight as this right-hand side. Assuming they're in the same spot, we're not going to go into like weird physics leverage stuff, but assuming they're on the same spot in the teeter-totter. You get someone on this side and it's completely balanced, you know they're the same weight. So let's take a statement like 3 is equal to 3, and let's look at it on our teeter-totter. So I'm just going to do 3 sort of equal size. We'll think of these as like all 1 pound little blocks. We got 3 on both sides. So what I can think about here is I'm going to think about this kind of from a gravitational standpoint. So if I were to think about what's going on here, well, we've got something pulling down, we'll say with like a force of 3, and something pulling downward with a force of 3. And these are exactly equal in terms of how hard they're pulling. So the teeter-totter doesn't balance, or doesn't go off balance. And we could look at some of our like balance method operations. We know we can add the same thing to both sides, subtract the same thing, divide the same thing, multiply the same thing. So let's just look at one, what happens when we add. So I'm just going to add one little block. Actually, no, this will be better. This will be a better example if I subtract. So what if I subtract? So I'll subtract 1. So I'm just going to go -1 from this side, -1 from this side, kind of like you're doing a balance method, and we'll use this teeter-totter to look at it. So I subtract 1 block from each side, and I just get, well, 1 block, 2 block, and 1 block, 2 block, which gives me the statement 2 equals 2. Still true. And so now let's look at kind of, if we're just with equal sign, what happens when we multiply or divide by a -1? Let's try multiplying by a -1. So I'm going to take the original equation. So we'll kind of subvert this one. I'll just box over it for a second. We'll kind of subvert this one, and that's fine. So let's go over here and let's just multiply both the left-hand side and the right-hand side by -1. So multiply -1 here, multiply -1 here. And I'm going to draw this in a different color. Let's say this blue block is like a -1 block. So -1, -1. And we multiplied 3 by -1, so we should get -3 on this side and -3 on this side. So what does it mean to have a negative block on here? So if positive weights were pushing down with a force of 3, this is like pushing up with a force of 3. So pushing up with a force of 3, pushing up with a force of 3, this will still be equal. So this is still true. So now let's take a look at what an inequality does, or essentially what it looks like to balance out something that's an inequality. So we're going to use our teeter-totter example again, and let's take, because we can also put things on this teeter-totter and it can show us inequality. So just like when this thing is flat, when this thing is slanted like this, it tells us something about the sort of comparative sizes or weights of these two objects. So let's take a number, like let's say you put 2 blocks on one and 1 block on the other. So let's take something like 1, 2, and I'm trying to make this realistic, because if you put 2 blocks on here, you would see that this side would go down. So you could say, well, this side being down says this is more and this is less. So this picture is essentially like the statement 2 is greater than, because remember it opens up to the greater number, than 1. So what we can do is we can also show kind of those balance method steps. And we'll see here that this is why this rule is coming in only in this case. So we could take this and we could apply balance method steps. So I'm going to move this to the side and we'll kind of try some operations. So take the statement 1 is greater than 2. And I could add something to both sides. So I'll draw my fence kind of like the center here. Draw my fence. Let's add 1 to both sides, and I get the statement 2 is less than 3. And we've checked it off. So that's just like taking, let's just take 1, 2, 1, 2, 3 to add 1, and we see that 3, that's still greater than 2. I could also take away. So let's go back and see, well, does taking away violate anything? Can we still do that? So I'll erase this. So let's take away 1 from each side. So let's say subtract 1 from the left-hand side, subtract 1 from the right-hand side, and we get the statement 0 is greater than 1. That's the same thing as saying let's take a block away from here so it's empty, take a block away from here from the 2 to get down to 1, and yeah, 1 is still greater than 0. We're still good. But let's see what happens now. And I'm going to go ahead and move this aside so we can just get like a clean slate. Let's see what happens now if I try multiplying. So I could say I'm going to double everything on both sides. So let's try taking both the left-hand side and the right-hand side, and we're just going to multiply it by, let me do this in a different color. We're just going to multiply it by 2. All right, so I do that, multiply the left-hand side, I get 2. Multiply the right-hand side, I get 4. 4 is greater than 2. That's like just doubling the size of both of these to where I've got 1, 2 on the left-hand side, 4 on the right-hand side, still true. Let's try multiplying now by a negative. So what I'm going to do now is I'm going to take that statement, 1 is less than 2. I'm going to multiply it by a negative and see what happens. So we'll multiply negative 1, negative 1. So I look at this and I get the statement negative 1 is less than negative 2. And if we think about this on my balance beam, is if I had this would be on the right-hand side, it'd be like pushing up with a force of 2 and pushing up with a force of 1. And that's how we kind of rationalize this being a negative 1, this being a negative 2. And you can see if you push up, this side would win. And we'd look like this. And we can also see from this inequality, negative 1, which on our number line is right here, that is not less than, it's farther to the right, so it's greater than. So kind of flipping it around the axis on this number line is kind of like flipping where we push on this teeter-totter. So you could see that this is not a true statement. When we multiply it by the negative 1, I'd have to flip the sign to look like this, because negative 1 or being negative 1 in debt is still having more money than being negative 2 in debt. So kind of rationalizing how you sort of navigate, I guess, distance from the number line versus magnitude, it's a little tricky. So if you get this, you're actually part of like probably 10% of the population. Most people get through Math 7 and they're like, I just memorized this rule. So let's take a look at an example now. Let's take a look at a few examples of this. So I'm going to start with 5.5 example 2. Again, if you feel like you need more bolstering on this, just go through that PDF. There's more worked out examples than the ones I'm doing. So let's take the inequality negative 3.4m, and I'll color code our m, is less than or equal to 17. So what I'm going to do here is I'm going to go about this normally, just balancing this out, but I'm going to keep in mind my rule that if I multiply or divide by a negative number, I have to flip the inequality. So let's look at our operation. So we've got a multiplication right here. Let's undo that multiplication with division. So what I'm going to do here is I'm just going to balance it out, divide both sides by negative 3.4. And let's just check. Did I get to a point where I have to apply my rule or not? I'm multiplying or dividing by a negative number right here. Dividing by this negative 3.4, I got to flip the inequality. So this has to go that way. That's my new rule in play. So negative 3.4 divided by negative 3.4, that just becomes, or it undoes itself and I just get m left over. And then 17 divided by negative 3.4, that gives me negative 5. And that's it. That's the new rule. So we'll go ahead and we'll plot it. So I'll put a number line down. We'll start at negative 5, and we know that could be a solution. M is greater than or equal to, so negative 5 is a possibility. So we'll fill that in to say it could be a solution. And then it also could be greater, so we'll just shade to the right. So now I'm going to give you one more example. And we're going to look at, and just to reference, if you want to reference it, is 5.6 example 1, just writing and solving some more complex equations, all while keeping in mind this new rule. So we're going to take a look at this example here where we're going to the craft store and we're going to buy some canvases and some paints, and we got a certain amount of money to do it. So we've got Hamish here, and Hamish has $25.97 in his pocket to spend at a craft store. And he wants to buy a paint canvas. So A implies he's only buying one of these. So he's not going to buy any more than one paint canvas and some paint pens. So sum implies that we don't really know. So we're going to say sum, and they kind of say it here, is going to be P. So P will specify it's going to be the number of paint pens. So we'll say it's like P amount. So he'll buy the canvas, one of them, plus the paint pens for $3.15 each. So let's answer a few questions that I think might help us set up this problem logically. So let's start. I'm just going to address the question, could Hamish buy more than $25.97 worth of supplies? So I think you can answer this on your own, but since this is a video, we're going to have to answer it through the video. We're going to say that's no, because that's the max. You can't spend more money that's in your pocket. They're not going to let you owe money to the craft store. And so, no, we'll say the max of $25.97. Can't owe the craft store. So next, let's just write an expression for how much Hamish is going to spend. So let's start. We've got $14 for the one canvas, and we're going to add on $3.15 for every pen that he buys. So now I just got to set this up into an inequality. So I've got the maximum Hamish can spend and the expression for how much he spends. So all we're going to do here is we're just going to take this expression, 14 plus 315 times P. So again, this is the expression for how much Hamish spends. And we're going to say that is going to be the maximum amount. So whatever is in Hamish's wallet, he has to spend less than that. So it's going to be less than or equal to what is in Hamish's wallet, $25.97. All right, and now we just go to town and solve this. So we've got all of our balance method tools in our tool belt. We're just going to apply them. So I'll just go ahead. We'll undo the order of operations, or we'll sad map it. So what I'm going to do here is we'll just undo the operation. So you can think of this as like a plus 14, and you could rearrange it where the plus 14 was at the end. But either way, we got to undo this 14. So we'll subtract 14 from both sides of the equation, or inequality, I should say. These 14s go away, and we're left with 3, and let's actually keep this color-coded so we can see where the variable is. And we're left with 315 times P is less than or equal to 25.97 minus 14, which should give us 11.97. Just a calculator operation or a mental math problem at that point. Finally, we just got to undo the multiplication. So we'll divide off by 315, divide by 315. And we'll check our rule. So let's just make sure, because there's a lot of times that you kind of misapply this rule. So let's check. If I multiply or divide, so I am multiplying or dividing by a negative number, but this is positive, so I don't have to flip anything. So I get 315 divided by 315, and I get P is less than or equal to, and if I do 1197 divided by 3.15, that'll be equal to 3.8. We'll go ahead and contextualize this really quick. So let's just look at what this let's plot it first, and then let's look at if we need to further contextualize it. So I get P is less than or equal to 3.8. So if we were to just plot this right off the bat, I'd get 3.8 here. And I say 3.8 could be an algebraic solution, so we'll fill it in. And then I got to shade it, see P is less than, so I got to shade to the left. And so this would be kind of the algebraic graphing of it, but we could actually bring in some context. So if I look at this context and I say, well, I've got this number line, and on this number line I have 3, I have 2, I have 1, I have 0, and I could even go to the negatives. But if I go into, like, there's a couple of situations where, one, if I went into a craft store and said, give me 3.8 pens, they'd look at you kind of funny. They'd say, no, I'm not going to cut a pen in half and get ink all over the desk. So you couldn't really go in and buy 3.8 pens, but you could buy 3, you could buy 2, you could buy 1, and you could also say, I'm just going to go in and not buy any paint pens at all. But I also couldn't say, at least, I don't know the kind of craft stores you guys are going to, but the ones that I've ever been to, I've never been able to go in and say, I want to buy -1 paint pens from you or sell you a paint pen. It's just not something that's going to happen. So more of a context-based solution, we could go here and say, well, the number line for P is 0, that's a solution. 1, that's a solution. 2, that's a solution. And 3, that's a solution. And so more contextually, we could say these are the possible pens Hamish could buy. So on that, if you have any questions on this, please bring it to office hours on Wednesday. I will see you guys later.